expectation of the sample mean. So very interestingly, expectation of sample mean is the population mean. Okay, and that means if we do many sampling, which we don't, but in theory, if you keep doing the sample doing 1 sample, 3 sample, 4 sample, 5 sample, we do many sampling, and we find the mean of each sample, and mean of all this sample mean, okay, will get you the population mean. So let me repeat. So you do 1 sample, you got a sample mean. Second sample, you got a second sample mean. First sample, you got a first sample mean. And mean of all this sample mean should be the population mean. Okay. So this nice property is called unbiasedness, but we will talk about this later. But this is a nice property to talk about. So consider we have 1, 2, 3. Okay, and this population has 3 numbers, and the population mean is 2. Okay, and now we consider sample size of 2. Okay, so how many sample you can have is 3C2, suppose, right? And if you have 1 and 2, right, the sample mean is 1.5, and you have 1, 3, the sample is 2, 2 and 3 sample is 2.5. Okay, and each of these sample outcome is appear equally likely, right? So the expected value of this is 1/3 of times this, 1/3 times this, 1/3 times this, and you can see it's 2, exactly the population mean. So that is the idea of mean of sample mean will be 2. Okay. So now we want to show you the proof of mean of sample mean population mean is using the linearity of expectation. So mean of sample mean is mean of the expectation of sample mean, right? Sample mean is indeed sum of the observation divided by n. This n can be taken out because n is unrelated. It's a constant, right? So expectation of sum of them. And we know expectation of sum is sum of the expectations. And expectation is each observation, right? Because it's a simple random sample. So we build a mu. So for n mu, right? N mu and n 1/n is cancelled out. So we have mu. So that's we show mean of sample mean is population mean.